everyone, welcome to part 1 of chapter 6. Today we are going to learn all about drawing Lewis structures for molecules, and we're also going to learn how to draw Lewis structures for polyatomic ions. So let's go ahead and get going. So the first thing we need to do is review how to draw the Lewis structure of atoms. If you'll recall, we talked about this earlier. Valence electrons, or electrons in the outermost shell of an atom, are responsible for the formation of chemical bonds between atoms. Remember, the way we can tell the number of valence electrons is we'll look at the group number. So for example, chlorine has 7 valence electrons because it's in group 7A. Remember that the representative elements, or the elements on the edges, are given the numbers 1 through 8. So it goes, 1A and 2A for the alkali and alkaline earth metals, and then we skip the transition metals and then start again with 3A with the group under aluminum. So you should get from 1A to 8A across the periodic table. Again, skip the transition metals. So the noble gases are in group 8A and have 8 valence electrons. So these Lewis structures are a simple way of representing the atoms and their valence electrons. Remember, we'll use the element symbol and the number of valence electrons to draw the Lewis structure for atoms. So this is what it looks like. So if we take chlorine, remember chlorine has 7 valence electrons because it's a halogen. So if you look at your periodic table, and hopefully you have it handy because you're going to need it for today's lecture. But if you look at your periodic table, you'll see that chlorine is in group 7A, which means it has 7 valence electrons. So you'll see we've put 7 electrons around chlorine. If you'll recall, we'll pretend like these elements are in a box. So if we put chlorine kind of in a box, the dots, right, that are representing electrons are going to go on the sides of the box. So for 7 valence electrons, we'll go 1, 2, 3, 4, 5, 6, 7. And obviously we don't actually draw the box. I just like to think of it that way so I know where the electrons are going. They have to go on a side. And you'll notice that I put 1 electron on each side before any got 2. So that's how we're going to draw Lewis structures, because that's going to represent our paired and unpaired electrons. If there are 2 on a given side, then those are going to represent paired electrons, and paired electrons are not involved in bonding. However, unpaired electrons, when there's only 1 on each side, those are involved in bonding. And so those are going to be really important to our drawing of Lewis structures in today's lecture. So you'll notice chlorine only has 1 unpaired electron, which means that chlorine is only going to make 1 bond. You'll notice though that carbon is in group 4A, and so it has 4 valence electrons. And remember, we're going to put 1 on each side before any get 2. So that's why we go 1, 2, 3, 4. And you'll notice that carbon has 4 unpaired electrons. This means that carbon can make 4 bonds, whereas chlorine could only make 1. Remember, unpaired electrons are involved in bonding, whereas paired electrons are not. These paired electrons, you will also hear them called lone pairs. So if you hear that, that's referring to paired electrons. We just typically call them lone pairs. All right, so hopefully you'll recall, but we've talked about the octet rule before. We talked about this earlier when we were talking about making compounds. We said that the whole reason that elements make compounds is to try to get to 8 valence electrons. They can transfer their electrons, like in an ionic compound, right? The metal cation is going to lose electrons and give it to the nonmetal anion, and that's one way of getting 8 valence electrons. And that's actually not what we're going to talk about today. The other way of getting 8 valence electrons was to form a covalent bond by sharing electrons, and that is going to be kind of the foundation of today's lecture. Okay, so when we form these covalent bonds, each atom is going to share some electrons and allow every atom in that molecule to obey the octet rule. So remember, the octet rule is that atoms will lose, gain, or share electrons so that all of the elements will get 8, which is why it's called the octet rule. But that's kind of the name of the game. When they have 8 valence electrons, this makes them isoelectronic with noble gases. This term isoelectronic may be unfamiliar to you. All that means is that it has the same electron configuration as a noble gas. So essentially what that means is that the atoms will lose electrons to become like their nearest noble gas, or they will gain electrons to become like their nearest noble gas, or they will share electrons to become like the nearest noble gas. So you probably are thinking, okay, well, what's cool about the noble gases? Well, remember what I just said. Noble gases have 8 valence electrons. So when we say they're becoming isoelectronic with the noble gases, essentially what we're meaning is they're having the same number of valence electrons as the noble gases, which is 8. So it's really just another way of phrasing this octet rule. By saying isoelectronic with a noble gas, it's saying they're going to try and get 8 valence electrons. So if we look at this example down at the bottom, remember each chlorine has 7 valence electrons. Okay, so here's one chlorine. So there's one, and then here's another chlorine. Okay, each of my chlorines have 7 valence electrons. However, they need to get to 8 to obey the octet rule. So what happens is these 2 chlorines will share these unpaired electrons. Remember, the lone pairs are not involved in bonding, so they can't make a bond. But these 2 electrons in the middle, they can make a bond because they are unpaired. So when they end up sharing that electron, this chlorine on the left thinks it has 2, 4, 6, and then 8. And the chlorine on the right thinks it has 2, 4, 6, 8. So by sharing these electrons, each chlorine thinks it has 8 valence electrons because it's sharing those 2 in the middle. Each chlorine kind of thinks that they, quote unquote, own the electrons that are in the middle. Pretty cool. So we're going to represent covalently bonded molecules as Lewis structures. It's really useful in this class for seeing how the atoms are sharing their electrons and learning a little bit about the shape of the molecules. We're also going to use these molecule shapes to talk about intermolecular forces. So Lewis structures is one of those kind of foundational topics in chemistry that we'll use to do a lot of other things. So make sure you're really understanding how to draw these Lewis structures as we're going through them, and make sure you get a lot of practice before you move forward in the lectures. Also, if you're going to go on in chemistry, or if you're going to take some biology, we use Lewis structures a lot in chemistry and in biology to talk about shapes of molecules and their interactions with each other. So this isn't just for this class. You may use it in other classes as well, but it is a foundational topic for this class as we move forward. So lots of reasons to get really good at drawing Lewis structures. Remember, our valence electrons are what's important here. So we're not using the total amount of electrons, we're just using the number of valence electrons. And pretty much we're always trying to get an octet, which means they're all trying to get 8 valence electrons. Our exception here is hydrogen. Hydrogen is going to try and become like its nearest noble gas, which is helium. Helium only has 2 valence electrons. So hydrogen actually doesn't follow the octet rule. Hydrogen follows the duet rule, which means that hydrogen is trying to get to 2 electrons. All of the other elements, though, are trying to get to 8. But keep this in mind that hydrogen is an exception. So when we share electrons, we can call them bonding pairs, or you can just call them shared electrons. But they're represented as 2 dots kind of while you're getting used to it, like we saw on the previous slide. But typically we represent a bond as a single line between the atoms. And you'll see me do that as we move forward. And then the non-bonding pairs outside of the bonds, right, the lone pairs, are placed on the outside. We don't draw lines for those. We only draw lines for bonding pairs. Lone pairs are just shown as 2 dots. So looking at this, couple different pieces of information we can get out of this. This is carbon tetrachloride, because you'll see 1 carbon and 4 chlorines. So this is CCl4. Okay, carbon goes in the middle, and we'll talk about how to figure out which one goes in the middle in a little bit. But carbon is the middle here, and so that's called the central atom. Okay, the ones on the edges, all of those chlorines, those are called terminal atoms. So the one in the middle, central atom, all the other ones called terminal atoms. And you'll see the electrons that are in the lone pairs, those are just represented by dots on all of these chlorines, right? You can see lots of dots. So our non-bonding electrons, or our lone pairs, are represented by dots. But our bonds here, right, these bonding pairs, they are represented by a line, okay? So don't represent lone pairs with lines, and don't represent bonding pairs with dots. We'll keep those kind of separate. So a lot of times when we are doing these Lewis structures, we will be forming single bonds. And in this slide, I'm showing them right now as dots, so you can see that each element has 8 valence electrons, except for hydrogen, which is only getting 2. So remember, hydrogen follows the duet rule. So the fact that each hydrogen has 2 electrons here means that it's complete, right? It's satisfied. Each of these fluorines has 8 valence electrons because we have 2, 4, 6, 8 for the fluorine on the right, and 2, 4, 6, 8. Oh, sorry, for the fluorine on the left and for the fluorine on the right. And the same thing for bromine and iodine, right? All of those are getting 8 valence electrons because they're forming a single bond here in the middle between those elements. So anytime electrons are shown like that between the atoms, that's indicating that they are bonding. But like I said, it's more clear to draw them as a line, so I will have you draw them as a line when we do Lewis structures. Like this. Okay, so instead we've taken these bonding pairs, and instead of making them as dots, we draw it as a line for all of these. Okay, and again, that just makes it more clear to show which electrons are bonding and which electrons are non-bonding. Sometimes though, our elements can form more than one bond between our atoms. So here, do you see that there are 2 lines between these oxygen atoms? That is called a double bond. Each bond represents 2 electrons, okay? So this is 2 electrons, and this is 2 electrons. So these oxygens are sharing a total of 4 electrons in these double bonds. This one, in nitrogen, this is called a triple bond because there are 3 bonds. So this is a bond, this is a bond, and this is a bond. Remember, in each one of those bonds, we have 2 electrons. So these oxygens are sharing 4 electrons in this double bond, and the nitrogens are sharing 6 electrons in the triple bonds, okay? But if you look, the oxygen has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. Or the nitrogen has 2, 4, 6, 8, and 2, 4, 6, 8. So no matter whether they're forming double bonds or triple bonds, they're still going to try and follow this octet rule. So like I said, multiple bonds can form when there's not enough electrons to complete our octets. Essentially what's going to happen is we're going to add up the total amount of electrons we're able to use in our structure, and if we run out of electrons before everyone has an octet, then we'll need to make double bonds and triple bonds in order to make those octets happen. Okay, and we're going to go through a lot of examples. So if you're a bit lost right now, that's okay. We're going to clear this up in just a minute. But like I was saying, in a single bond, we share 1 pair of electrons, so that means we're sharing 2 electrons. In a double bond, we're sharing 2 pairs of electrons, so 4 electrons total. In a triple bond, we're sharing 3 pairs of electrons, which means we're sharing 6 electrons. Okay? So here's some rules for drawing Lewis structures. We're going to go through this a lot, so you probably won't need to reference these rules, but if you like to have something to reference, now's a good time to screenshot this, take a picture, pause so you can write it down, whatever you need to do so you can reference it later. All right, so our first step is we are going to figure out the molecular formula. Sometimes I will give you the name of the compound and you'll need to write the molecular formula. But for now, I'll typically give you the molecular formula while we're getting going. But using the molecular formula, we're going to write the symbol for each of the atoms the way you expect them to be arranged in the molecule. This is referred to as drawing the skeletal structure. So step 1, draw the skeletal structure. The one that's going to make the most bonds will be the central atom. Okay, and we're going to figure out in just a minute here, how do we know which one can make the most bonds? But for now, just say, okay, whichever one can make the most bonds, that's going in the middle. Our rule here, hydrogen can never, ever, ever go in the middle. The reason for this is hydrogen can only make one bond, ever. The end. So we can't put it in the middle because it can only make one bond. So that's a good rule to remember. But otherwise, the one that can make the most bonds will go in the middle. Our next step is to figure out the total number of valence electrons from all of the atoms in the molecule. So that means you're going to need to have your periodic table to figure out how many valence electrons each atom has. Then we'll add them all up to get the total number of valence electrons in the molecule. Our next step is we're going to use valence electrons to form bonds between the central atom and all of the outer atoms. Remember, every bond is 2 electrons. So we're going to kind of remove those electrons for our electron count as we go. And then our last step will be to use any remaining electrons to complete our octets. Or if we don't have enough octets, or enough electrons to make an octet, then we'll start making double bonds and triple bonds. So, like I said, how do we know which atom goes in the middle? The one that makes the most bonds will go in the middle. So the way that we figure this out is the honk rule. Hydrogen and all of the halogens, remember the halogens are in group 7A, they form one covalent bond. So typically, our halogens will not be central atoms. Also, our hydrogen, like I told you before, can't be. So since these guys only form one bonds, it would be pretty weird if they were a central atom. Oxygen and sulfur, right, these are both in group 6A, can form 2 bonds, and that should make sense to you because if they have 6 valence electrons, they need to form 2 more bonds to get to 8, right? So oxygen and sulfur form 2 covalent bonds. So this can be a double bond or 2 single bonds, but that's good to keep in mind. Our next one is nitrogen and phosphorus and anything else in group 5A, right, form 3 covalent bonds. Again, if they have 5 valence electrons, it makes sense that they need to get 3 more to get to 8. So this can be as a triple bond, 3 single bonds, or a double bond and a single bond, right? However, it makes 3 bonds. And then lastly, carbon and silicon are in group 4A. They form 4 covalent bonds because they need 4 more electrons to get to 8. So this can be 2 double bonds, 4 single bonds, a triple bond and a single bond, a double bond and 2 single bonds, right? It doesn't matter as long as they are making 4 bonds. I will tell you here, there is no such thing as a quadruple bond. So nothing's ever going to make like we talked about nitrogen makes a triple bond. Nothing's going to make a quadruple bond. So just kind of put that out of your mind. But this is the honk rule. So hydrogen and halogens make 1, oxygen makes 2, nitrogen makes 3, and carbon makes 4. So you can remember this as honk 1, 2, 3, 4. Okay, I like to give you little ways to remember things. So the honk rule will help you remember which atom goes in the middle. Remember, the one that makes the most bonds goes in the middle. So if carbon is in your atom, carbon is going to go in the middle. If not, maybe nitrogen or oxygen will go in the middle. All right, let's go ahead and try this out. We are going to draw the Lewis structure for phosphorus trichloride. So our first step is to figure out which one goes in the middle, right? The central atom is phosphorus because it can make the most bonds. So if we go and we think about the honk rule real quick, phosphorus is in group 5A, and you'd be able to figure that out if you were looking at your periodic table. But phosphorus is in group 5A, which means it can make 3 bonds, whereas chlorine is a halogen, and that means it can only make 1 bond. So phosphorus goes in the middle because it can make the most bonds. So that's why you see phosphorus here in the middle and the 3 chlorines on the outside. It doesn't really matter where you put these chlorines, just kind of evenly space them around your atom. Our next step is to figure out the total number of valence electrons in your molecule. So what we do for this is we go figure out how many valence electrons each atom has. Okay, so phosphorus, because it's in group 5A, it has 5 valence electrons. So we have 1 phosphorus times 5 valence electrons. That's giving us 5 electrons from phosphorus. Chlorine is in group 7A, and there are 3 of them. So if we multiply 7 by 3, we get 21 electrons coming from chlorines. So total, we have 26 electrons that we can use in our structure. Again, 5 from phosphorus and 7 from each of the chlorines. So if I add them all up, we get 26. Our next step is to attach each bonded atom to the central atom with a pair of electrons. So remember, we started with 26 valence electrons from that previous slide. Each bond counts as 2 electrons. So this is 2, 4, 6 electrons that we used up attaching the chlorines to the phosphorus. So we'll subtract out the 6 that we used making bonds, so we have 20 electrons left that we have to use in our structure. So our last step is to use our remaining 20 electrons, right, that we have left to complete our octets. So just be careful here that you don't use more or less electrons than you're allowed to. Okay, so we went, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we've used up all 26 electrons now. 6 of them in the bonds, 20 as lone pairs. Okay, and our last step is to make sure that every atom has an octet. So like chlorine over here has 2, 4, 6, 8. This chlorine has 2, 4, 6, 8. Oops, don't think of that as a double bond. This chlorine has 2, 4, 6, 8, and phosphorus has 2, 4, 6, 8. So all of these atoms have a complete octet, and we use the correct number of electrons in our structure. So always double check both of those things before you decide that you're done. Let's try some more. So the first one is methane. Okay, and remember, we need to figure out first which element goes in the middle. If we think about the honk rule, carbon can make the most bonds here because it can make 4 bonds, whereas hydrogen can only make 1. Also, remember I told you hydrogen can never go in the middle, so it's definitely got to be carbon here. So we'll put carbon in the middle and our 4 hydrogens around the outside. All right, now we need to figure out how many valence electrons we have to play with. So we have 1 carbon, and there are 4 electrons in each carbon, right? If you look at carbon has 4 valence electrons, so that will give us 4 from the carbon. We have 4 hydrogens, and each one has 1 valence electron, so we're getting 4 from the hydrogens, which means we have a total of 8 valence electrons we can use in this structure. Our next step is to connect all of the outside atoms, those peripheral atoms, we connect those to the middle using bonds. So we use up 2, 4, 6, 8. So we subtract 8 from 8 and we get 0 left. Okay, so our structure is done. All we need to do now is make sure every element is satisfied. Remember, all of our hydrogens only want to have 2 valence electrons, which means that they should just be making 1 bond. And as you can see here, each hydrogen is just making 1 bond, so that's good to go. Our carbon, though, needs to make 8 valence electrons, and you'll notice it has 4 bonds going to it, and each one is worth 2 electrons. So we have 2, 4, 6, 8. So our carbon is satisfied. So that's the structure of methane, CH4. Alrighty, our next one is chlorine, Cl2. So a lot of times people get stuck here and they're like, wait, what's the central atom? Well, do you see there's only 2 elements, right? There's only 2 chlorines. So we're just going to go ahead and put them side by side. There's no central atom here because there's just the 2 of them. Our next step is to figure out how many valence electrons we have to use. We have 2 chlorines. Each one has 7 valence electrons because they're halogens. So we have 14 electrons total that we can use in our structure. So the first thing we'll do is connect them with a single bond. So that used up 2 electrons. So now we have 12 left that we have to use. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so now I've used up all 12 of my electrons. There's none left, and I just need to make sure that each one has 8. So this chlorine has 2, 4, 6, 8, and the chlorine on the left has 2, 4, 6, 8. So that's a good structure. All of them are satisfied with the octet rule. Let's try another one. So this is water. So water, remember again, we're following the honk rule. Oxygen can make 2 bonds, whereas hydrogen can only make 1. So that's why oxygen will go in the middle. Okay, I'm going to draw this like this, and I'll explain why in just a minute, as soon as we finish this structure. Okay, so there's my oxygen in the middle and my 2 hydrogens. So now we need to figure out how many valence electrons we have to use. So we have 1 oxygen that has 6 valence electrons, so that will get us 6. And we have 2 hydrogens that each have 1 valence electron, so 2 total from the hydrogens. If we add them together, we get 8 electrons that we need to use in our structure. If we connect our hydrogens to our oxygen, that uses up 4 electrons, because remember, each bond is worth 2. So we have 4 electrons left. I'm going to put all of the rest of those electrons on my oxygen because my hydrogens don't accept lone pairs. Remember, hydrogen just wants to form 1 bond, so it can follow the duet rule. So I put all of those electrons on oxygen. Now I just need to make sure that everything is satisfied. So each of the hydrogens has 1 bond, just like they should, and oxygen has 8 valence electrons, just like it should. All right, so that's a good Lewis structure. So a lot of times people will ask me, okay, well, why did you make the hydrogens do that, right? Why didn't you do this? Okay, as you can see, there are 2 bonds, right, still going to hydrogens, and there are 4 unbonded electrons on oxygen, so 2 sets of lone pairs. So essentially, right, they're like, okay, well, aren't these things the same? Well, kind of. They're kind of the same. The problem is we're going to get into molecule shapes in the next lecture, and these would actually have very different molecule shapes. And they'll also have different properties when we start talking about intermolecular forces. So it's actually really important to draw water with this bent shape than with this linear shape, because the linear shape is going to make you know all kinds of wrong things about water. Water is a bent molecule, and we're getting into, like I said, a lot in the next couple lectures. So make sure you draw water with this bent shape and not with this linear shape. But anytime you draw something with oxygen, it's always going to be bent like this. The reason is, if you think about drawing the Lewis dot structure for oxygen, remember oxygen has 6 valence electrons. So if I was to space them around my oxygen and put them on one on each side before any get 2, we would do this. 1, 2, 3, 4, 5, 6. And my lone pairs end up next to each other. As long as you always go in a circle, whether clockwise or counterclockwise, it doesn't matter where you start. But if you put these electrons on in a circle, then the lone pairs will always be next to each other. So I use that to help me remember that oxygen has a bent shape. Similarly, sulfur will also have this bent shape because it also has 6 valence electrons. Okay, so when you have things with oxygen or sulfur as central atoms, make sure not to draw them as linear, but to draw them instead as bent. All right, let's try our next one, carbon dioxide. So thinking about the honk rule, we have to figure out which one goes in the middle. Carbon can make more bonds, so that one goes in the middle. So I'll put carbon here and my oxygens on either side. Okay, so by now people are like, wait, okay, hang on. You made oxygen, this water molecule has a bent shape, but why didn't you make carbon dioxide bent? Well, the reason for that is that carbon has only 4 valence electrons. And so it can make bonds on kind of any side of the carbon, whereas oxygen and sulfur have 6 valence electrons, which changes the shape of the molecule. More on this, though, in the next lecture. Okay, but since carbon can make 4 bonds, it'll be a linear molecule like this. Okay, so now we have to figure out how many valence electrons we have total to use. We have 1 carbon, and each carbon has 4 valence electrons, so we get 4 from the carbon. We have 2 oxygens, and each one has 6 valence electrons, so we're getting 12 from our oxygens for a total of 16. Okay, so we're going to connect our oxygens, so that used up 2, 4. So now there's 12 left. All right, so let's say we did this. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, I used up my 12 electrons, but if you look at this, there's something wrong, right? Each of the oxygens has an octet, right? They each have 8 valence electrons, but look at carbon. Carbon only has 4 electrons going to it, 2 from each of the bonds, right? 2 here, 2 here. So this is not a good Lewis structure because carbon does not have 8, right? Everyone has to have 8 in order to satisfy the octet rule. However, we can't just add more electrons, like we can't put lone pairs on carbons because we ran out. We only had 12 more to use. We could only use 16 total in this whole structure. So we've run out of electrons, but carbon doesn't have an octet. So what do we do now? So what we do is instead of these lone pairs belonging to oxygen, we take one of those lone pairs and we share it with our carbon. So if we do that, then it'll look like this. Okay, so one of those lone pairs is now shared with the carbon and made a double bond. So now carbon has 3 bonds going to it for a total of 6 electrons. So we got closer, but we're not quite there. So what we're going to do is we're going to take a lone pair from the other oxygen and share it as well. So it'll look like this. So looking at this, each oxygen now has 2 lone pairs and 2 bonds for a total of 8 electrons. So nothing changed about the electrons belonging to oxygen, just instead of sitting up here as lone pairs, we ended up sharing them with the carbon. But either way, oxygen is still kind of gaining the benefit of those electrons, so each of the oxygens still has 8. However, by sharing those electrons, we now also allow carbon to have 8 valence electrons as well. So now this is the structure of carbon dioxide. All right, let's try some more. So this is ammonia. Again, remember the honk rule. Okay, so nitrogen will go in the middle because nitrogen can make 3 bonds, whereas hydrogen can only make 1. So we'll put nitrogen and then our 3 hydrogens. It doesn't matter which side you put the hydrogens on, just kind of space them around. So now we'll count up our total valence electrons. We have 1 nitrogen, and each nitrogen has 5 valence electrons, so we're getting 5. And then we have 3 hydrogens, each with 1 valence electron, so 3 from there. So now we'll connect our hydrogens. That gives us a total of 8. Now we'll connect our hydrogens to our nitrogen. 2, 4, 6. So that means we have 2 electrons left to use. The only one that doesn't have, isn't satisfied right now is nitrogen, so we'll put both of those electrons on nitrogen here. Remember, no lone pairs ever on hydrogen. So now nitrogen has 8 valence electrons, and each of the hydrogens has 2. So this is a good Lewis structure. Our next one is oxygen, O2. So again, there's no central atom here. We'll just put our oxygen atoms side by side. Now we see that we have 2 oxygens. Each oxygen has 6 valence electrons for a total of 12 electrons in our structure. So if we connect them, that got rid of 2, and we have 10 more to use. So if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll notice the oxygen on the left-hand side has 8 electrons, 6 in the lone pairs and 2 in the bond. However, the oxygen on the right only has 6 electrons. So what we do here is the same thing we did with carbon dioxide. We'll just take one of these lone pairs and instead we'll go ahead and we'll share it. So that will make a double bond between the oxygens, and then each of them will have 2 lone pairs. Alrighty, let's try another one. This is nitrogen. So N2, again, neither one of those nitrogens is, the central atom. We'll just put them side by side. We have 2 nitrogens. Each nitrogen has 5 valence electrons, so we have 10 total we can use in this structure. So we'll connect them here. That got rid of 2, and we have 8 more to use. So we'll go 1, 2, 3, 4, 5, 6, 7, 8. Looking at this, you'll see, oh wait, one of the nitrogens has an octet, but the other one only has 4 valence electrons. So let's go ahead and start sharing. Remember, the reason that we can't just add more electrons is because we are limited by the number of valence electrons in the molecule. So always double check that you don't use more electrons than you're allowed in your structure. That's why we count up these electrons at the beginning so that we know how many electrons we can use. All right, let's go ahead and share a pair of electrons. That will allow it to look like this. All right, so now the nitrogen on the left-hand side has 8 electrons. Still, nothing has changed, but the nitrogen on the right now has 6. However, it doesn't have 8, so we have to keep going. So let's go ahead and share another pair of electrons. So when we do that, we're going to form a triple bond between the nitrogens, and then each nitrogen has 1 lone pair. Okay, now each nitrogen now has 8 valence electrons, and we've satisfied the octet rule. Okay, so again, make sure you're not using more electrons than you're allowed in your structure, and if you ever run out before all of the atoms have an octet, just start making double bonds and triple bonds to get them there. All right, this is our last one. Let's try ethane. So again, remember the honk rule. Hydrogen can never go in the middle, so carbon will, but there are 2 carbons, and that trips some people up. So what we do when there are 2 carbons is we'll put those 2 carbons side by side. So essentially there's 2 central atoms here, and we'll put the hydrogens on all the edges. Alrighty, now we need to figure out how many valence electrons we can use. We have 2 carbons, and each carbon has 4 valence electrons, so we get 8 electrons coming from the carbons. We have 6 hydrogens. Each one has 1 valence electron, so there are 6 electrons coming from the hydrogens. This gives us a total of 14 electrons we can use in our structure. So now we need to connect all of the atoms together. So we'll go 2, 4, 6, 8, 10, 12, 14. So we've used up all of our electrons. But if you look, that's okay because each of the hydrogens has 1 bond, just like it should, and each of the carbons has 4 bonds, just like it should. So that all worked out very well, and there are no lone pairs in this structure. Couple things to note. Just talking about the number of bonds as it relates to the bond strength. The more bonds you have between 2 atoms, like a double bond versus a single bond, the stronger those bonds are. So more bonds equals stronger bonds. Okay, so like double bonds are going to be stronger than triple bonds. I like to think this as arms holding these 2 together. If you have, a double bond, then there are 2 arms holding the atoms together, and that's going to be stronger than just 1 arm holding the atoms together. So that's how I think of it. Also though, the more bonds you have, the shorter those bonds are. So a double bond is going to be shorter than a single bond. I like to think that with those 2 arms, I'm pulling those atoms in closer together because it's a stronger bond, which makes them closer together. So stronger, shorter, more bonds. Weaker, longer, fewer bonds. Okay? So double bonds are shorter and stronger than single bonds. All right, I want you to go ahead and try this out. Try to draw the Lewis structure for nitrogen trifluoride. So pause here, give it a go, and then come back when you're ready to see the answer. Alrighty, the first thing we need to do is figure out which atom goes in the middle. Remember the honk rule. Okay, so nitrogen can make 3 bonds, whereas fluorine can only make 1 because fluorine is a halogen. So nitrogen will go in the middle here. So we figure out how many valence electrons we have to use in our structure. We have nitrogen will give us 5, and then we have 3 fluorines, and each fluorine has 7 valence electrons. So 5 plus 21 gives us 26. So when we connect each one of these fluorines to our central atom here, that's going to use up 2, 4, 6. So that's going to give us 20 electrons left. Okay. Then we're going to go ahead and finish off our structure by adding in our lone pairs. So you'll notice in this structure, I have added 20 electrons, and I didn't need to create any double bonds or triple bonds or anything like that. I was just able to go in and give each atom enough electrons to complete the octet. So that's it. Let's try another one. I want you to draw the Lewis structure of CH2O. Remember to use the honk rule to figure out which atom goes in the middle. So go ahead, pause here, and then come back when you're ready to see the answer. Alrighty, thinking about the honk rule, we see a carbon, so carbon is always going to go in the middle if there's a carbon. So carbon will go in the middle, the two hydrogens and the oxygen will go around the outside. Doesn't really matter where you put them, just as long as they're not in the middle. Alright, so then we can add up all of our valence electrons. We have one carbon, two hydrogens, and an oxygen. So 4 plus 2 plus 6 gives us 12 electrons we can use in our structure. We used up 2, 4, 6, making bonds, which means we have 6 electrons left. Okay? If we were to try, and I'm going to draw this over here, if we were to try to finish our octet, we would go, okay, 1, 2, 3, 4, 5, 6. Which is great for oxygen, but you'll notice carbon only has 6 bonds going to it, or 6 electrons going to it, 3 bonds. And so the way that we remedy that is we take one of the lone pairs from oxygen and we share it to the carbon. So it will look like this instead. Okay, so there's going to be a double bond going to the carbon so that the carbon has 8 valence electrons around it, and the oxygen also has 8 valence electrons around it. Alrighty, let's get some practice on this. Go ahead and pause here and complete problem number 1 on the Chapter 6 lecture worksheet so you get some practice drawing Lewis structures. When you're done, come back and we'll keep going. Alrighty, so thus far we've drawn the Lewis structures of neutral molecules, but we can also draw the Lewis structures of polyatomic ions. So if you'll recall, we had to memorize some polyatomic ions for our chapter on nomenclature. Okay, so polyatomic ions are just a group of atoms with an overall charge, but essentially they're covalently bonded molecules. They just happen to have a charge that goes along with them. So drawing the Lewis structures of these polyatomic ions is going to be very similar to drawing the Lewis structures of molecules. The only thing different here is we've got that charge to deal with. Okay, but when we have polyatomic molecules or polyatomic ions or other complex molecules, there's often more than one possible way to arrange the atoms. So that's going to be a little bit different here. There's more than one correct Lewis structure. Whereas all of the structures we've drawn before, there is a specific right answer. Usually when we have a polyatomic ion, you're going to figure out which atom is different and put that one in the middle. So you're going to look for the unique atom. So like if we were drawing the Lewis structure for phosphate, the phosphorus is the different atom, so it will go in the middle. Where like sulfate, sulfur is the different atom, so it would go in the middle. So whichever one is different, it's usually not oxygen, whichever other one you have, that's going to be the one that goes in the middle. Then we're going to put the other atoms around the outside and draw our bonds just like we've done before. And we'll take into account that charge in just a second here. So let's do an example. Let's draw the Lewis structure for nitrite, NO2 minus. Okay, so the thing we're going to do first is we're going to arrange the skeletal structure of the molecule. If you'll recall, I told you to put the unique atom in the middle. So in this case, it would be nitrogen. A good rule of thumb, though, is don't put oxygen in the middle if you have a polyatomic ion, because oxygen can only make 2 bonds, and so it's not a very good central atom. So we'll arrange our skeletal structure of the molecule. Then we are going to add up the valence electrons. So we have 1 nitrogen, 2 oxygens, and then do you see this +1? you'll notice, like, what is that plus 1 doing? Because the 5 came from the nitrogens, the 2 times 6 from the oxygens, and this plus 1 is from this minus charge up here. Okay, so you'll notice it's plus 1 for the negative charge, not minus 1. The reason for this is that negative charge means there is 1 extra electron. So we need to remember that electrons are negatively charged. And here, when we are adding up the electrons, so that negative, that means there's an extra electron, that ends up being a plus 1 here to say, okay, we have 1 extra electron in this molecule. So be super careful there, okay? Negative charges mean you have extra electrons, whereas positive charges means you lost electrons. So it's kind of counterintuitive. So we have 5 from the nitrogen plus 12 total from the oxygens plus that 1 extra from the negative charge gives us 18. So then we're going to, we have 18 and we're going to subtract out 2, 4 from our bonds just like we normally would, which means we have 14 electrons left to use in our structure. Okay. Now we're going to add pairs to complete each atom's octet. So if we look, we used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that means this is a good Lewis structure because we've used up all of our electrons and all of the atoms have an octet. But now you're thinking, wait, no they don't. Look at nitrogen. Nitrogen doesn't have an octet. Okay, so this is just like we've done before, where when we run out of electrons, we have to make double bonds, right? Looking at this though, does it matter which oxygen I pick to donate the electrons to nitrogen? Could the oxygen on the left donate them just as easily as the oxygen on the right? And the answer there is yes. So in this case, I form, these electrons should have gone away. My apologies. But in this case, we're going to take these electrons and donate them to the nitrogen. Okay, so the oxygen on the right has 1, 2, 3, 4, 5, 6, 7, 8. And the oxygen on the left also has 8. But you can see that I could just as easily have picked the oxygen on the left to donate the electrons as the oxygen on the right. So how do we know which one's correct? Well, the truth is they are both correct. So in this first one here, the oxygen on the right-hand side donated its valence electrons to form that double bond and give nitrogen the octet. But in this one on the left, our left oxygen donated its electrons to form the double bond to give nitrogen the octet. So in both of these different scenarios, all of the atoms have an octet, but they are two different Lewis structures, right? So which one is right? The truth is, they're both right, and kind of neither, but we'll get into that in later courses. Okay, but for now, we're going to say, okay, there are two different Lewis structures that can represent this molecule. When we have more than one Lewis structure that can represent a molecule, we call these resonance structures. Okay, so more than one correct Lewis structure that can be given for a molecule is called a resonance structure. So let's try this one. Draw all possible Lewis structures for carbonate. So again, we'll recognize this as a polyatomic ion. And most of the time, polyatomic ions have resonance structures, which means that more than one correct Lewis structure can be drawn for this molecule. So thinking about the honk rule, or the rule that I told you earlier that the unique atom goes in the middle, that means that carbon will go in the middle here. Okay, so we'll put carbon in the middle, and we'll put all of the oxygens around the outside. Then we're going to add up how many electrons we have to use. So 4 from the carbon, 6 from each of the 3 oxygens, and then remember plus 2. That 2 minus charge tells us we have 2 extra electrons to use, so we're adding 2 electrons to our electron count. Okay, just remember, electrons are negative, so they're going to be added when we're adding up our electrons. So we have 24 to use. We've used up 2, 4, 6, by bonding the oxygens to the central atom, which means that we have 8 electrons left. So if we gave all of the atoms an octet, then we would, run out, because we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But if you look at carbon, carbon doesn't have an octet. Carbon only has 6 electrons. So that means we need to donate a lone pair to make a double bond with the carbon. But as you can see here, it doesn't matter which oxygen we picked. We could pick the oxygen on the right, we could pick the oxygen on the left, we could pick the oxygen on the bottom. So each one of those oxygens will give us a different resonance structure, because that structure will look a little bit differently. If it's double bonded to the oxygen on the right, that'll look different than the one bonded to the left or the one double bonded down. Okay, so in this instance, we made the double bond with the oxygen going down, right? But like I said, it could have been any of these oxygens that made that double bond. So for carbonate, there are actually 3 different Lewis structures. You can double bond it to the carbon on the left, to the oxygen on the left, to the oxygen above or below, depending on how you've drawn it, or the oxygen on the right. So there are 3 different Lewis structures for this compound, which means there are 3 different resonance structures. Okay? Resonance structures, like I said, are just when you can draw more than one Lewis structure for the same molecule. You'll also notice this bracket here. Okay, so the bracket like this, with the charge on the outside, that's what we do for polyatomic ions. So anytime we are going to draw the Lewis structure of a polyatomic ion, we are going to put the entire Lewis structure in brackets, and we're going to put the charge on the outside. That's saying that in this molecule that I drew, there are 2 extra electrons that I'm using. Okay, and again, we got that 2- from up here. But putting it in brackets and putting the 2- outside is saying, like, if you add up all of the valence electrons and add 2, that's how many electrons are in this structure. So you'll see here for the resonance structure, each different molecule, right? Each different Lewis structure is in brackets with the charge on the outside. Also, anytime we draw resonance structures, we draw these double-headed arrows between them to show that they are resonance structures. So it's essentially saying carbonate could look like this, or it could look like this, or it could look like this. Okay, so we're going to draw the Lewis structures, put them in brackets if our molecule is charged, and then draw arrows to show that they are resonance structures for each other. Alrighty, we have wrapped up today's lecture on drawing Lewis structures for both neutral molecules and polyatomic ions. We talked about the honk rule and how that helps us know which atom goes in the middle. It's very important to count up the number of electrons that you can use in your structure to make sure that you either use all of them or don't use more than what you're allotted for. If you run out of valence electrons before each atom has an octet, you're going to need to go back through and make double bonds or triple bonds to make sure you meet that octet rule. Remember, for polyatomic ions, a lot of times they will have resonance structures, which means we can draw more than one Lewis structure for those molecules. For each resonance structure, though, we're going to put the entire thing in brackets and put the charge on the outside to show that that molecule isn't neutral. It's charged, which means we're using a couple extra electrons. And then we're going to use arrows between the different resonance structures to indicate that they are resonance structures of the same molecule. So we covered a lot of ground today. Make sure you do problems 1 and 2 on your Chapter 6 lecture worksheet to get really good at drawing Lewis structures. We are going to use Lewis structures not only for the remainder of this chapter, but also for the remainder of the course when we talk about properties of molecules. So you're really going to need to be good at drawing these Lewis structures. Get lots of practice, and as always, if you have any questions, please feel free to reach out and ask me for help. Remember, I teach chemistry because I like talking about chemistry, and I especially like drawing Lewis structures, so I promise you're not bothering me if you ask me some questions. Otherwise, keep working hard and get lots and lots of practice. I will talk to you guys next time.